will start as a chair.
Perfect. Okay. Okay, thank you. Makoto has some information on tonight's banquet.
Okay, so I announce the banquet again. So tonight, this evening, we have a banquet from 7:30 p.m. and the place is Grand Nikko Tokyo Daiba Hotel. It is about 10 minutes walk from here. And the room is underground, not going up, underground. And as already mentioned, students who have presentations, both oral and poster, are invited. So please register at the LOC desk and take a banquet ticket. Okay? Yes.
And let me just reiterate that if you're a student and you've got a paper or a poster, you're invited at no cost to the banquet. And if you've already paid, you can get a refund at the desk. But we do need you to register at the desk if you're coming. Thank you very much. I think that's it. Okay, so I think now we'll turn it over to Victoria to start off the next session.
Hi, good afternoon, everyone. So we're going to change themes just a little bit. With all the data, the modeling, the observing, et cetera, it all will ultimately, hopefully, feed into how we decide what to do next. This session is a little bit of a grab bag, but you'll see various perspectives on that. Okay, these papers are 15 minutes. We will set the timer for 12 to give a little bit of warning and then time for questions. Our first speaker of the afternoon is Avishai Melamed from the University of California, San Diego. Thank you.
Go to the next slide. Yes. Okay. Hi. So. Oh, right. In here. Oh. Hi. So today, thank you. Welcome to the politics and process of planetary defense. We're going to be covering our study along with my co-author, Melamed. Where we covered the full range of political and mitigation options available to a decision maker before, during, and throughout a deflection campaign. So with some background, we start with the general trend that throughout any deflection timeline in a generalizable format to all NEOs, but also to PDC 17, where throughout the timeline, the longer we have to observe a near-Earth object, the more sure we can be of its orbital path, and therefore the requirement of a mission to deflect it. But the longer we wait, the longer it would take to deflect and more difficult it would be to deflect the object. We especially like this trend since even though the decisions correspond to phases within the timeline, it's especially useful in PDC 17 since it neatly lines up with the scenario's 3 launch opportunities. So also special thanks to the Aerospace JPL team for providing the NEO Deflection app, which we used in our study. So as you can see, there are 3 launch opportunities throughout the decade-long exercise, around 1250 days apart, each iteration requiring more and more investment to successfully deflect the PDC object. And so we calculated the cost in commonly used US lifters and the experimental SLS. We also considered an iron equivalent, despite that being absent from the original exercise, simply to demonstrate the overall trend of the difficulty of deflecting extremely dense objects. As you can see, it's a significant investment. To make it a little easier and quicker to read, we put it in this format, showing that if we wait for a late phase in the timeline for true confirmation, we may at times be risking sometimes up to 5 times the investment of an early campaign. So, since lifters, including but comparable to the Atlas V and Delta IV, are available today, the question of planetary defense instead changes to a matter of conducting the most efficient campaign at the most reasonable cost, either by launching early on, or as we'd like to discuss, by coordinating an international effort. International coordination promotes a more reliable campaign, providing us with greater resources and more options through the existence of infrastructure that's readily available before a NEO threat and therefore a campaign even begins. Specifically, this would allow a deflection campaign to conduct early launches in a reasonable format and also conduct late launches regardless, while compensating for the cost with greater resources. We'll delve into that. So today, in the current geopolitical atmosphere, of the 193 recognized UN member nations, there are only 10 who currently retain the capacity to conduct launches into space. And only 5 of those, plus one supranational organization, have demonstrated the capacity to successfully conduct interplanetary scale launches in the vein that would be required to deflect a near-Earth object. So this leaves the vast majority of nations in the world vastly underdefended. And as we've seen in recent years with the Chelyabinsk event and other near-Earth objects that have passed below near-Earth orbit, below lunar orbit, even nations that are capable of conducting deflection campaigns cannot individually defend the whole world. So bringing together these interests would fulfill the security needs of both at a much greater efficiency. Of course, by providing resources from more members, we can lower the orbital uncertainty much more quickly and compensate for the rising costs of a later campaign. And this is especially useful since in the current climate, most international cooperation is limited to the sharing of information, such as shared databases of near-Earth objects, their locations, and statistical information. But we believe that this could be significantly improved to enhance our deflection capabilities if we worked further. So most likely, this would consist of joint funding and sharing of personnel and equipment between cooperative nations. This would ensure that future crises are not handled in segregated formats and gives us the most options by providing us with more resources and lifters and personnel, while at the same time limiting the cost to specific members by spreading out the effort between as many willing contributors as possible. So, of course, we'd like to also look into a unified international front that passively monitors threats over time, much like the current sharing of information, but could be activated to conduct a deflection campaign jointly from the beginning to save as much time as possible, which is pretty, as you know, pretty vital throughout a deflection campaign. Of course, with all the benefits of international cooperation come several political considerations. The first being the question of Westphalian sovereignty, or the concept that that a country ultimately has the ultimate right to dictate its laws and considerations within its own borders. But as we all know, near-Earth objects do not take political considerations into mind and do not respect the concept of international borders. So the question is how to respect sovereignty while keeping in mind the territorial interest of participating member nations. So the solution we've come up with is international coordination. This is especially relevant in PDC 17, as we considered early on in the timeline whether, as you all know, there was the question of if the object threatened the countries bordering the Sea of Japan, whether or not to launch east and to launch west. And so the question of what would happen if, for example, China launched eastward and Japan launched westward, or vice versa. And so this is a kind of dilemma we'd like to avoid by forming a uniform effort. Of course, the choice of participation has to lie with the participating nations themselves, and of course, keeping in mind that countries have security considerations, we recommend delegation of personnel and sensitive information and equipment to be worked by those nations themselves to preserve their rights. then we come to the dilemma that planetary defense is ultimately a collaborative effort. For all its benefits, every nation that participates in planetary defense has an incentive not to comply with planetary defense measures. So this manifests in a game theory concept we like to call the prisoner's dilemma. There's two specific formats in which this applies here, the first being between two spacefaring nations, as for example, the US and China in this event. The problem is that today we are currently in a state of mutual defection within relations on this, where all spacefaring nations are largely expected to conduct deflection campaigns on their own and pay the full costs of conducting such a campaign alone. And also, each nation would ultimately prefer the most that they defect and the other spacefaring nations comply, hoping that that another nation could conduct the campaign and keep them safe without having to pay the cost. But ultimately, the desired norm of international coordination and cooperation is that both nations would pay limited costs in the state of mutual compliance. Again, costs are spread out between members, and we could also conduct a much more efficient and effective defection campaign with more resources available and more personnel working. Then, of course, there's also the equally complex situation of where the majority of these interactions are between spacefaring nations and non-spacefaring nations, where here we're currently the standard is a standard state of where the spacefaring nations comply with international coordination, but non-spacefaring nations defect. The expectation is that that large nations are fully capable of defending non-spacefaring nations without those nations contributing to such a campaign. And again, we'd like to recommend that that we pursue a state of mutual compliance here too, where even though non-spacefaring nations cannot necessarily conduct a deflection campaign on their own, they are definitely available and capable to provide assistance with such campaigns, either through funding or personnel or equipment, launch locations, et cetera. And so their cooperation would manage to, again, spread costs and allow us to conduct a more effective campaign. Ultimately, this points to the problem that that planetary defense is a collective action problem, where it is within the interest of any nation on the Earth to allow another nation to conduct a planetary defense campaign and shoulder the burden alone. However, the global nature of planetary defense, both in terms of the damage it could cause and the potential benefits that would come from working together instead, shows that working along the free rider thought process is rather inefficient. So today our options are largely limited to these two, either to allow over 90% of nations in the world to get by without adding to the deflection campaign, or alternatively, we could seek international coordination where both nations would shoulder proportionate costs and overall contribute to a more effective campaign. Of course, this does come with the risk of defections, as nations still will have the incentive to leave a cooperative effort, possibly once they find that they are no longer under threat. So we can bypass that either through imposing audience costs. We can make sure those nations are held accountable through compulsory contribution, so that even if they leave, their investment does not, or by tying them to norms of reciprocity, which is a little risky, involves transnational advocacy networks, and usually works over a much longer course of time and is not feasible, but in the long term may be useful. And of course, we could provide incentives for nations to cooperate regardless. Membership can be solicited to low-risk nations or even nations that cannot conduct deflection missions on their own, based on the possibility that future threats will threaten them, or that they will be indirectly threatened by the consequences of not assisting a current deflection campaign. So early investment in such a joint mitigation effort requires that we preserve the ability to assure such nations that their contribution will lower the overall risk of impact in the future and improve their ability to respond to partial and failed deflections. So in summary, recognizing the significant rise in cost that comes with waiting to conduct a later campaign, we'd like to reserve the ability to launch as early as possible, and while also looking into preserving our effective understanding of orbital certainty and uncertainty. And so the challenge is to set up a global planetary defense entity that meets our security needs without compromising the rights of nations and making sure that their contributions stay intact. Keeping these measures in mind, we believe that global coordination and cooperation is the best way to achieve an efficient, secure, and practical defense campaign. Thank you. Let's go to questions.
Thank you very much, Avi. Do we have any questions for our speaker? Yes, we have one here.
So you talked a lot about international planetary defense and nations, but did you ever consider in the analysis private entities kind of coming into play in this mix, and what you kind of see there?
We did consider that in the paper, but at this point, it's a little hard to measure. Of course, being directly invested in this business, those private organizations have a direct incentive to comply with the planetary defense effort and could, in fact, facilitate such an effort by providing equipment. So, but specifically, they do not operate along political lines, and so while we consider their potential benefits, they are not the primary focus of this study.
I think we have to move on.
Oh, okay.
Thank you again.
If you have any questions, I'll be there at the break.
Okay, great. Thank you. Thank you again. Our next paper is by Nahum Melamed. They are related. NEO Impact Mitigation Decision Steps and Triggers.
Thank you. I'm going to describe a little bit more technical aspect to what was just said and connect it with a talk that was given yesterday about a tool that was developed at the Aerospace Corporation for the concurrent engineering system design for planetary defense. And so Aerospace had a group of about a dozen summer hires last year that we employed to build a tool that could be interfaced with the NEO Deflection app that we designed together with JPL, and use it to derive the information that is needed for the concurrent engineering tool, the concept design center that Aerospace is employing, and then connect it with the kind of decisions that could be taken before a threat is presented at the time of discovery and then alongside the threat. And so this is just a status update on the ongoing effort with our summer hires. And what we want to do is to continue with a new group of summer hires this coming year and cover the following range of decision making. The pre-discovery phase, decisions that should be taken at the time of discovery, and then decisions that can be taken during the evolution of the threat that are directly connected with what was decided at the pre-discovery phase. And so we'd like to apply that end-to-end decision process to the tabletop exercise, the TTX 14. Paul Chodas just presented the TTX 16 details, and we had another one in 2014, which was very similar in nature, and also applied to the very initial phase of the 2017 scenario that was before the details of the current scenarios were revealed, and so this is going to be preliminary. Obviously, the basic elements of deflection campaigns are the payloads, the launch vehicles, And so we would like to be able to design such payloads that are going to fit into the system that is necessary to deflect an object. That's what we'd like to do. And then, ideally, to manufacture some of these systems and put them in storage so that they can be used at a time of need. This is our goal. A key decision driver is obviously the cost. That's something that is usually the most difficult part of deciding whether to go ahead with any solution. And so we took an analysis that we've done about 10 years ago and updated it to 2017 numbers. And it's quite obvious from those plots that any payload would cost many hundreds of millions of dollars, depending obviously on the mass that needs to be lifted to the object. And launch vehicles are also in the range of many hundreds of millions of dollars, up to perhaps about $1 billion for the SLS if it is necessary. So these are expensive endeavors. These are not decisions that are easy to take, not in advance and not in real time, whether to spend a few billions on something that is not totally assured. Obviously, if a decision is applied prematurely, we are going to spend these kind of sums on a mission that might not be necessary at the end. Or if we wait too long, and the threat had confirmed, we might end up with needing a lot more resources, and it's going to be costly on that side. So that's the dilemma. That's the decision-making dilemma. Are we using the minimum amount of resources that are necessary and decide early and risk not using it at the end, versus waiting and needing a lot more resources and a lot more costly campaign that might have low degree of reliability relative to what was done in advance. And so there are many decisions that could be taken. A few obvious ones are listed here. For example, wait until the next launch opportunity. This is a decision that can be taken at the time of discovery or at any launch opportunity downstream. Just wait for the next opportunity and gather information using ground and space assets. You could also launch a characterization mission and get better information from in situ observations, which is in many cases a good thing to do. But again, it's a mission that might cost some money to do, and somebody has to allocate those resources for a characterization mission. Additionally, we could just act early and launch a system to deflect a potential impacting asteroid and perhaps abort the mission if the mission becomes unnecessary. Or we could just do nothing. We could do nothing because maybe there is insufficient time to do anything, or perhaps because we just don't have the capability to do anything. We just didn't develop anything in advance. Or there's just disinclination to do anything when the impact likelihood is very, very small. Are we really going to spend this kind of sums on something that has 1% or 0.1% or whatever decision is in the mind of the decision maker should be the trigger to actually go ahead with allocating the resources for a system. The first tool that we used, obviously, was the Deflection app that was developed in collaboration between Aerospace and JPL. Besides the educational value of the tool, it also provides attainable deflection solutions, ballpark solutions that can tell you what is feasible in terms of deflecting an oncoming asteroid with a kinetic impactor. And we developed, or the group of students that stayed with us over last summer, developed an interface tool that runs the Deflection app at a particular region of parameters and extract the best solution from it and feed it into our automated concurrent engineering tool that was described yesterday by Aaron Reeves. I'm not sure if he's still here or not. But we had a talk that described how the tool is used to design several elements of the deflection payload. And so what we do is we apply these two tools to the 2014 scenario and the 2017 scenario. This is a summary of the 2014 scenario, about 7 years to impact, a similar size object to what we are experiencing in this conference. And it was decided to launch six kinetic impactors, 3 US and 3 international. The missions were successful in intercepting the asteroid, but a fragment was still undeflected and hit the Earth. So that was just the detail of the scenario. What could we do to design the payload that would actually be placed on a launch vehicle and conduct this kind of deflection? So we went back to the Neo Deflection app that includes a feature that's called Deflection Maps. It tells us the opportunities to launch and deflect the asteroid. And those columns of colors are those opportunities in terms of the launch date from the Earth and the intercept time with the asteroid. So we picked a few little segments out of the deflection app to be explored with our automation tool, and ran the tool and identify those regions that are feasible for launching a kinetic impactor to the asteroid. And these are the regions that are marked with green here. These are all attainable regions for launching a deflection campaign or a deflection mission in that case. And that tool extracts the necessary information for the concurrent engineering tool to be able to design the payload for this particular mission. So every time we would change anything in the mission design, we will extract a different set of information that would go into a multidisciplinary design tool. And then we began doing the same kind of thing with the 2017. You are familiar with the parameters of the current threat. We went to the same deflection app and extracted some of these parameters. Obviously, the first opportunity to launch is not available to us because nothing was developed ahead of time in the pre-discovery phase, and so this opportunity is out of consideration. The next opportunity will be in about 1,200 days. So if we decide to do anything, can we build it now with adequate reliability and expect to launch a series of missions to deflect the oncoming asteroid? It's a big question. And we need to see what would be the payload that would actually do that. Are we able to build a payload that can be deliver the amount of momentum and impact to the asteroid? And so in conclusion, we need to make the kind of decisions that will give us the maximum flexibility when emergency situation develops. If we develop the capability well ahead of time with a modest investment, then at the time of need, we will have a capability or the option to decide to launch something when emergency actually occurs. Today, we don't have that. So this is the pre-phase situation. And what can we send is identified by these kind of tools, right? I mean, can you build that? Our tool will tell us whether we can actually go ahead and build with current technology what is necessary to launch. So this is part of the extended study. We're going to refine it with additional elements in the coming summer, evaluate another range of hypothetical scenarios, and that's going to be carried out by the new group of summer hires that are coming to visit us in the coming year. Thank you.
Thank you, Nahum. Do we have any questions?
There's certainly some truth to better, faster, cheaper. I just point out the kind of missions we want have got to work, and they've got to be done fast, and that suggests very expensive.
Absolutely. It's going to be very expensive. The premise is that you can spend some of the money before the emergency, have it tested, so that when you need it, it's actually available for you to use. So absolutely, I mean, it's expensive is the name of the game here. But the cost of not doing anything is probably even higher. So the idea is that spend early, and you will have some options later on down the road.
Any other questions? Thank you again.
Thank you.
The statement was smart project management. So our next paper is given by Joseph Nuth of the NASA Goddard Space Flight Center, titled Short-Term Threat Response Requires Long-Term Preparation.
Well, half of my talk has been given already over this conference, and that's fine. Let's see. This is the first thing to say. I want to make sure that everybody knows this is not NASA policy. This is myself, Ron Leung, and Brent Barbee's ideas. And so there are two goals of this presentation, at least for me. First, we'd like to convince the community that comets should be taken a little bit more seriously by this community. I think they've been mentioned once or twice, but that's pretty much it. The trick is that dangerous comets, not Jupiter family comets that we can predict the orbits decades, centuries in advance, they're short response time objects. And obviously short response time things have a lot in common. We'd like to actually then make a series of recommendations, some of which are already made here, to defend against short response time comets or asteroids. And of course, getting a consensus view from this community is probably the first step in that direction. All right, I'd like to suggest that detecting asteroids and mitigating their potential for impact is really kind of easy compared to cometary impacts. Mostly threatening asteroids travel in well-behaved orbits, just like PDC 2017. We know where it's going to be to within error bars decade in advance. And it's unlikely that 100-kilometer asteroids are going to show up out of nowhere nowadays. That's still possible with a comet. Relatively minor changes to an asteroid's orbit, of course, when imparted early enough, can make a big difference. But the problem with short response time items is you don't have decades or centuries to do something about it. Perfect example of this is Comet Siding Spring. Comet Siding Spring was detected in January of 2013. It buzzed Mars at 135,000 kilometers distance in October of 2014, 22 months after discovery. We're having really hard times with PDC 2017 in 10 years. 22 months basically is pretty much impossible to do anything about it now. And part of the reason, of course, is that if you sort of look at the normal build schedule for reliable, high reliability planetary missions, they take 5 years. And there's a good reason for that, basically. There is no doubt in my mind, or in our minds, that we can cut that schedule down significantly. There's slack in there, there's plenty of review, there's plenty of design studies. All that got put in for a reason to make sure that the system works. The problem is that everything that you cut out of that increases mission risk. And although you actually want a planetary spacecraft to do its job, you don't really want a high-risk mission, I would contend that planetary defense is the thing that you want the absolute highest reliability spacecraft actually attempting to save your planet. All right, the problem with Siding Spring, of course, is that it dropped into the inner solar system from the pole, the ecliptic plane, 90 degrees to the ecliptic plane. So the approach velocity was much faster than a typical asteroid. In this particular case, rather than roughly 20 kilometers a second and less, it approached Mars at 56 kilometers a second at the time that it passed closest. Since collision energy is proportional to v squared, this is roughly an order of magnitude more energy. And I would contend that high relative velocities for comet collisions aren't that unusual. One of the things that I'll use to argue about that is that we can look as a great proxy for potential comet collisions with a planet to meteor showers. For those of you not familiar with meteor showers, basically They're the debris that comets shed as they go around the sun. They stay in that exact same orbit so that, roughly speaking, each meteor shower represents a potential collision with a comet that never occurred. So I went to Wikipedia because it had the most complete list of annual meteor showers that I could find. The relative velocities range between 3 and 71 kilometers a second for the various cometary sources, and they're here in alphabetical order. The red denote the relative velocities greater than 60 kilometers a second. That orange color is greater than 50. The yellow is greater than 40. You can see most meteor showers have significantly higher relative velocities than the typical asteroid impact that we would see. Only 6 of those have velocities under 6 kilometers per second. So, if you look at the relative dangers from asteroids and comets, the number that I've heard bandied about in terms of what the relative threat is in terms of impacts is roughly 100 to 1. Namely, you're going to get hit by 100 asteroids before you get hit by 1 comet. On the other hand, comet impacts are much more energetic. You're probably going to have roughly a factor of 10 more energy based on the velocity of a comet. And the second thing is that comets are much bigger than the typical asteroid that's going to hit you. You don't see a 30-meter comet. They are gone. You see maybe a 300-meter comet as a small version, something like Hartley 2. You see maybe a 30-kilometer comet, but you usually don't see, the 30-meter comets. So comets are roughly 10 times more energetic because of velocity, 10 times more energetic at a minimum because of their mass. So they have 100 times the destructive potential of your typical asteroid collision. So if you look at destruction versus destruction of comets and asteroids, I'd say half of the destruction threat to the Earth is due to comets. The other half, in much smaller increments generally, is due to asteroids. And on top of that, comets, of course, provide much less warning time from discovery to impact than do typical asteroids. All right, so we come to our recommendations. I think this one is pretty obvious based on this exercise. We need to cut down the time from discovery to launch of doing something. And one of the ways of doing that's fairly simple. You build an interceptor spacecraft, as the previous speaker had said, and you put it into storage. This has been done before. Al Gore had a satellite called Triana that he wanted to launch. We built that satellite. Political winds changed. We put it into storage for a while, more than a decade. And we've now launched it as the Discover satellite, and it's working fine. So there is no problem with storing satellites for a particular amount of time. The launch vehicles, on the other hand, are being produced all the time. So what you really need is the specialized payload in storage, and you can, at warning, go out and try to find a launch vehicle. That's not so hard. I would say because if you're doing this for a comet threat, you're looking at something large, you make sure that it can carry a nuclear explosive device. You don't have to load it on there if it turns out to be a relatively small object, say a sneaky asteroid that managed to come in that's small enough that a kinetic impactor works. That's fine. You put dummy mass in there and you use it as a kinetic impactor. The point is that it has the targeting capability to be able to intercept that particular object on a relatively short time scale. So I also note at the bottom that NASA never deals with the nuclear device. That's always in the hands of the people who know how to deal with it. I thought at the time that I prepared this talk a couple of months ago that I was going to have to convince you that you're going to need a characterization spacecraft. The obvious answer was the fact that Rosetta thought it was going to the object on the left. It actually went to the object on the right, and the shape of the particular target is important. I don't think I have to convince you of that anymore. We're doing it. So the second part of the recommendation is we're going to build the interceptor, but we also probably need to build a simple observer spacecraft. We can use the observer to do the things that are listed here. I also suggest that we build backups to the interceptor and the observer spacecraft, and you continuously modernize all these particular spacecraft over time. You can release the older models for science uses at some point in the future. That's relatively straightforward. I have the rationales for doing this, but as I said, I think those cases have been made fairly well over the course of the exercise we're doing and over the course of a whole variety of previous speakers. And so the bottom line on this one is that if you have a stored payload ready, we can launch that most likely within a year of the determination, probably within 6 months of the determination that we have to do something. The interceptor is, like I said, the nuclear armed system that could handle large objects. You don't want to rush the design. I think that's one of the reasons Paul has. Several of the spacecraft that we have sent in this exercise are casualties of that. 2 didn't get built and another one's failed. I wouldn't doubt that a third one fails at some point or other. So the observer spacecraft are all obviously highly desirable. Backups are desirable to take care of that. And building spacecraft at a low level with improved systems just basically makes sense until we don't have to. The way to look at this problem, I think, as more along the lines of the way we're sitting here. We have a fire suppression system. Nobody wants to use it, okay? We don't want the fire suppression system to have to go off. On the other hand, if there's a fire in this building, we don't want to come in and have to install that fire suppression system in order to put it out. So this is something I think that can be relatively simply communicated to politicians. You're basically building a defense system for the Earth that we never want to use at a very low level of cost. We found out that our politicians over here threw the kitchen sink at it. $8 billion was nothing compared to the trillions that they were losing. So we need to make those arguments. And again, I will end with that one. So thank you very much.
Thank you, Joe. Any questions? I see one down here.
Thank you for bringing up comets as an issue. There's a poster on mitigating comets with directed energy, which is actually quite useful against even very large comets. There's an example of the 60-kilometer one, for example. Comets are quite different, and as you say, they're both fast and they're quite stealthy. But the other issue is they're harder to mitigate against with traditional techniques since they move so fast. And also, you really have to go through the simulations to see how well a impactor would work. I don't think it will work very well at all.
Oh, I don't think an impactor on a comet's got a chance in hell.
Yeah, good, thanks. But I actually think when you run the case for a nuclear weapon, you'll find it's not so easy either. Mm-hmm. And so I think there needs to be some detailed studies done on that.
No, I agree. And that's one of the reasons why I want the community to actually start taking them a little more seriously. We're not running any simulations on comets that I know of. They pop up occasionally in a poster session or whatever, but that's about it.
Further questions? Here's another one.
Hey, Joe. I agree completely. I've been looking at comets for a long time as well, and I'm just, it's really more of a comment that I think it's really good to show it from an energetic level rather than a pure numbers, because obviously the number of long-period comets and potentially other trans-Newtonian objects that could find their way into the inner solar system is smaller, but the size, the speed, the amount of damage that they can do is on par with the asteroid population when aggregated over a long period of time. So again, we've got a long-term problem. This is maybe a longer-term problem, but it could be even more catastrophic than asteroids.
And one more short one behind.
I'm sorry, I most strongly disagree. The risk from comets is a couple of orders of magnitude less than the risk from asteroids. That's because there are less comets and they have much longer periods. So the probability of impact are less, and there are also less of them. So
It's the difference.
I'm not saying the comets are not relevant, but first we have to eliminate 99% of the risk from asteroid, then we can take care of comets.
It's the difference between getting hit by a BB and an elephant gun. I'll take 99 shots from a BB. Just don't hit me with the elephant gun.
Yeah, just a couple of points. One is that we have done the best we can to assess allowing for differences in density, size, velocity, and everything else. And that 1% number claims to account for all of those things. Now, we could be wrong, but on the other hand, if you look to the moon, for example, you see that mostly it's asteroid impact. The other point that I wanted to make, though, is the matter of having a nuclear device at the ready in case you need it sometime. I wrote a paper along with Carl Sagan, Greg Canavan of all people, and Steve Ostro in 1992, addressing that problem. We called it the deflection dilemma. And in that, we suggested that if, Al Gore's satellite sat in the barn for 3 years or something, if you're only going to need it once in 1,000 years, you have to consider what might happen to a nuclear device that might fall into the wrong hands. Suppose a world leader turned out to be a madman.
The answer to that.
Okay,
The answer to that is the NNSA already has them, and they're the ones that keep them, and they don't put it on the ship until launch.
thank you. Thank you. We're going to move on now. Thank you. Thank you very much, Joe. Our next presentation is by Ed Liu of the B612 Foundation. Did I get that right, Ed? Yeah,
Yep,
B612.
that's right.
Okay. The distribution of required deflection impulses is a function of time before impact of Earth impacting asteroids.
Afternoon, everybody. First off, I wanted to just thank the conference organizers. I've had this conversation now with a number of people beforehand. We've all been amazed at how far this field has come over the last, I don't know, it's been 15 years since the first one, I think it was. So thank you for helping do that. It's, the field has matured a lot, and each one of these gets better, so thank you. This is some work that we've been doing with some of my colleagues at Space Exploration Engineering and at Google. And what we wanted to look at is what are the distribution of deflection requirements needed, not just the sort of quote typical cases or the cases that we pick for PDC conferences and so on, but what are those distributions? What do they really look like? So, what's the range of deflection cases that you get? What are the what are the stressing cases? Either they're artificially chosen by Paul, or that nature throws you, or as opposed to the typical cases. What's most likely to be seen by us? What's most likely to end up as a deflection decision? What's most likely to be presented to itself? And how does this change with time before impact? So to do this required a bit of computational capability. So what we did was we took the population of virtual impactors from Peter Verish and Steve, wherever you're sitting up here somewhere. And what we did was which is, for those who don't know, what they did was they took population of NEOs and selected out of them those, a population of 10,000 of those that actually hit. So it's consistent with the NEO population, but they have a slightly different distribution. And then what we did was we verified that they actually do impact if you take them and run them forward. And what we did was we ran them then backwards in time so that we had a database of these where you had an initial orbit at least 50 years prior to impact. And then what we did was we asked the question, well, how much delta V does it take to make each one of those miss as a function of time before impact? And we ran a targeter on each of these at various times prior to the impact to look at just how much delta V it took. So this is all independent of mass, right? You can scale these things by mass, but we're just looking at the delta V. And that allowed us to generate plots of these distributions. And what you get is kind of interesting. So first off, what went into this? We had to generate an orbit propagator. We've done that. We include, just like JPL does, the planets, the large asteroids, general relativity. We parameterize Yarkovsky, et cetera, et cetera, et cetera. And we've tested our results against a number of test cases. So this is just showing that we can do that. In general, we can run most of these asteroids forward over a period of many decades and still remain within, in most cases, well under a kilometer. So either they're making a mistake or we're both making the same mistake or whatever it is. But we believe that we're doing this accurately enough and we're within sort of numerical noise at this point. Our targeter, how does that work? So when we are looking for the delta V it takes to make it miss the Earth, what we just decided to do was to do basically a little differential corrector. So it'll find what velocity increment is needed to get to a point. And what we artificially did is we chose, let's just assume we want to get to a point 10 Earth radii away from the Earth. That's completely arbitrary, 10 Earth radii. Truthfully, if you miss the Earth by a tenth of an Earth radius, it's not hitting, but let's just pick a number, and we could use other ones. And then we applied this targeter. So it's an iterative thing. It's like a ray shooting method. This shows you an example. The white line, ignore the gray line. That's the Earth. That's the moon's orbit off in the background, because the software just displays that. The white line is the original impactor, and after you apply the targeter and then run it forward, you see that this is just our test to show that it does miss by 10 Earth radii. And you can do this at a couple of hundred time steps for each one of the 10,000 asteroids. And what do you get? The typical case looks like this. So this is years prior to impact, so this one goes from 0 to 16 years, but we actually took this out to 50 years. And this is the delta V in meters per second. So the general trend here is obviously the closer to impact, so down near 0, the more you need to shove something to make it miss the Earth. You see this orbital effect due to perihelion, aphelion, but this is the general trend. And we repeated this 10,000 times. And so I just want to show you what a typical histogram looks like. So this is 30 years prior to impact. So what I'm plotting here is just the histogram number of cases versus this is in meters per second. So this, you can look at this as 2 centimeters per second, 4 centimeters per second, 8, and so on. And 10,000 cases. I'll tell you later what the blue and the red is, but you'll see that there's a sharp peak down here near almost 0. And a broad distribution centered around approximately 1 centimeter per second. Okay, and so you'll often see, quote, typical values of if you plug in the numbers for those, you get something like this is entirely consistent with those typical values. Right, it's of order of 1 centimeter per second at 30 years. Okay, but it's pretty broad. Okay, so what's going on here? Maybe it's easier to sort of talk about this. There's a really long tail out here of asteroids that require a lot more than typical. So 4 or even 8, quite a factor of several more than average. And these, if you take a look at them, are cases where in general the asteroid hits the Earth but running parallel to the Earth. So in other words, it's kind of running into it from behind, or the Earth's taking over and running into it. Right? So if you think about the geometry of that a little bit and ask yourself, let's say I sped up or slowed down that asteroid by a little bit, what you find is that you actually just delay the impact or make it slightly earlier. So it becomes less effective. It's sort of geometrically tougher cases to miss the Earth. Because if you think of it as like the Earth is a car driving down the highway and you're overtaking it, changing your speed just doesn't make you miss the car. It makes you hit it at a slightly different time, as opposed to a perpendicular case where the Earth is coming down as a car driving down the road this way and I'm going the other way. If I change my speed a little bit, I get a timing and I miss the Earth coming through the intersection because I'm there at a different time. Those are cases like this. There's also an interesting set of cases down here at very low delta V, and those are kind of what you think they would be, which are those with intervening close approaches. So we took a look at each of those individually, and so they require in general more than an order of magnitude less delta V, so now think like a millimeter per second. What we did is we just ran these things and we put a little flag in there. If at any point in time between the initial part of this and the impact, the asteroid came within a Hill radius of any planet. And you look at those, and about 5% of those, a little more than 5%, do meet that criterion. A couple of them have several, but almost all these were Earth close approachers, as you would expect. And then what I did is if you look at this, we color-coded in, how do I get back here? In blue, those that had the flag of close approachers. So these ones really are those that had close approaches, and so that's not surprising at all. We all kind of knew that, but it's interesting. You can sort of see now that in general, it gives you more than an order of magnitude decrease in deflection delta V. So if you just pull that subset out, there were 518 out of the 10,000, you get this. And so now note the scale is down in now millimeters per second. So quite a bit less. But what we want to point out is that those asteroids that have very small deflection delta Vs are also, because of that, those that are most difficult to ascertain if they're going to hit the Earth. The ones where the probability distribution is difficult to narrow down because they have a close approach. They're apophyses, if you'd like, right? After the close approach, you spread out the uncertainty. Interesting, though. So these are the ones that are going to be, in some sense, are going to dominate your decision cases because they're ones that you can't throw off the risk list as easily, right? Because of the fact that they come very close to Earth, that also makes them radar targets. So one of the arguments that we want to make is regarding the importance of radar data, because the very set of asteroids that is most difficult to determine if they're going to hit the Earth is also the very set of asteroids that comes close enough for you to get a range measurement, a range and range rate measurement from radar. Again, this is that, we wanted to look next at just how overrepresented are these in the in terms of the difficult decision cases. So what we're actually working on right now is we're going to take this one step further backwards. We are going to actually look at the expected distribution of impact probabilities. So we're going to run a large simulation with these impactors with a telescope model and actually do an orbit determination on them and look at the impact probabilities and how those change with time as you get closer to impact. We'll hopefully report on that within a few months. I will add one last thing, which is that these various tools that we've been building are cloud-based, and due to our friends at Google, we are building this system to be able to run very, very large numbers of these types of analysis problems. And these are things that we might be able to help other researchers with by opening them up. So if there are those interested in talking about that further, I'd be happy to talk about that. So thank you.
Thank you, Ed. Thank you. Questions? I see a hand down here.
Hi, Ed. Nice talk. So isn't what you're describing for the very low delta V cases, aren't those basically keyhole cases?
Yeah, you can call them that. They are keyholes.
So when they make their close pass and you get good radar on them, isn't it too late? I mean, they've already made their pass, and so now the delta V isn't low anymore.
Some of them have more than one, first off. But yes, that is an issue. But that doesn't mean, in general, you might be able to get another. Remember, we set our flag at only 1 million miles. Okay, and you can get a radar pass further than that. So what we haven't looked at is we haven't modeled in, for instance, how far can you reach it as a function of size and whether or not you could have gotten an earlier shot. We'd like to be more quantitative about this, and we will be.
Hi, Ed. This is a really neat tool. It appears to me that the delta V vector is calculated to be whatever it needs to be to successfully move the asteroid.
In this particular case, yes.
Right.
You could have constrained it in other ways, and we can do that
Well,
too.
that's what I was going to suggest. I think it would be cool to, and maybe you guys have already started doing this, I don't know, but it would be cool to run a case where, this would require a lot more computation, but it sounds like you're not short on CPU cores, where you modeled the trajectories from Earth to the asteroid for kinetic impactors, for example. Because in that case, the available delta V vector is just going to be what it is, and you don't really have much control over it. And we could do the same ensemble data generation that you did, but with that constraint in play. It'd be interesting to see how that shakes out.
Yeah, that's a great idea. And the way that we're architecting the system is such that you should be able to write modules that can plug into this.
That's great.
So we should talk about that.
Yeah, let's talk, because I can think of several things that I'd like to do with that.
Yeah, and we want to make the system open in that way, so that depending upon what people are looking at, they can sort of tailor it to what they want.
Okay, let's thank our speaker. Thank you, Ed.
Okay, so we will continue with the next presentation, which will be given by Fabrizio Bernardi, and the title is Impact Corridor Visualizer Tool for ESA.
Ladies and gentlemen, good afternoon. So today I will present the part of the results of a contract that we did recently with ESA, and so this is also the acknowledgement of this contract, of course. And let's start with the motivation, the research background. So because ESA is going through this SSA program, Space Situation Awareness Program, since 2008, there is a tool that was missing, and the tool is the one that is computing the impact location. So ESA was requesting this to the European community. So SpaceDis, with a consortium that is including Electrodemos, IFAC, CERCO, was awarded of this contract, and we also, because we benefit of this long time know-how in the orbit determination and impact monitoring activities, and then we of course start using the NEODIS data, actually also for consistency, because the NEODIS data are also shown by the NeoCC portal. A bit of mathematics. Of course, our team is well known to have used what's called the semi-linear method. So we wanted to adapt this method to this computation, to this tool. And we started actually with the impact monitoring data, as I said before. We have, with this, we have a full least square solution. We take the virtual impactor representative, that is a set with the orbital parameters that are for a virtual impactor that is going to hit at a specific time. Then what we do is actually propagate this virtual impactor to the time of the impact and to the altitude above the surface that we want to consider. Altitude that is going from 0, ground, to 100 kilometers, that is just on the top of the atmosphere. Together with this, actually, we propagate also the covariance. So we have also information about the uncertainty. At this time, we take the representative curve, the ellipse, at some confidence level, sigma, that is going from 1 to 3 to 5 sigmas. We sample this ellipse, and then we propagate non-linearly starting from this curve. And this way, we actually compute the position on the considered surface. Okay, this is a simple data flow architecture. We have the NeoDis data. We take the via representative. We compute the impact corridor. Then we put the data into a data sharing archive in PISA. And then through this, let's say, sharing interface, we send the data to the NEO Coordination Center. And this NEO Coordination Center will give the information to the decision maker, and hopefully she will make a better decision than man. Okay, so let's start with a real example. Of course, it's good good. Yeah, we had a real example that didn't make any damage on ground. We know 2008 TC3. We know exactly where it happened. We have several evidence on that, and actually we found the real meteorites. Okay, this is how it looks. We are using the Google API for the 2D representation. Fortunately, or unfortunately, depends on the perspective, this was in the desert of the Sudan, so there are no roads that are shown on this plot. But here you can see not only the map, but there is a console on the left side where actually you can play with it. Unfortunately, I was not able to load the video that Marta Ceccaroni was very well preparing, but unfortunately it's not working on this computer. You can select different confidence level, and then you can, for example, print your view, your image. You can save your image, and another thing you can do is actually visualize the satellite view. That is easily to see. The color code that we are using here for the ellipse is that red is 1 sigma, then there is orange 3 sigma, and then yellow is 5 sigma. There is one other thing that is shown on the lower left corner is this button that is allowing you to download the KML file. So you can not only use the 2D map of the Google API, but also you can use Google Earth. Okay, just continue with the example. This is the plot in Google Earth that we can have with only the first 12 observations of 2008 TC3, so only 2 hours and 20 minutes of arc. As you can see, the uncertainty was very huge. If we can zoom on the real location of the impact, you can see that the 1 sigma uncertainty region was actually very close to the real one. But after 4 observations later, so only a few observations were needed to increase a lot of the precision of the accuracy of the prediction. Now we have 8 hours of arc, so we could already determine that it was not going to impact in a big town or so. And then, using all 859 observations, with the arc was almost 19 hours, so just the last observation was just 1 hour and something before the impact. We could really determine the impact location. Here we have on the right side, on the right side here, we have the nominal impact location. If it was supposed to be like a big object, it was going to impact over there. But of course, we know that it's plotted on flight, and we have here the map of all the meteorites that were found during the exploration. And here is a comparison between our results and JPL results that were provided by JPL team. And as you can see, we are both very well consistent with the meteorites that were found during the exploration. So yeah, this is another case. This is a nasty case, as you know, because 2014 AA had only 7 observations. In this case, the linear approximation is not working very well, but because we have very few information. In this case, actually, the ellipse was kind of twisted, and it's not really easy to explain, in particular to a person that is not expert in this field, easy to explain this kind of figures. So the lessons that we learn from this is that, first of all, we need more observations. And this is why it triggered later on, after this discovery, that both JPL and also NEODIS started this imminent impact tool that are actually scanning on real time the NEO confirmation page. And second is actually be careful, because this object was discovered during the New Year Eve. And this is a very well-known Murphy law for applied to NEOs, because they're always going to be dangerous when people are busy with other stuff, as you know, with Apophis. And finally, this is a synthetic object provided by Paul Cholas. as you know, and we did the same computation, and you can see that they are very well consistent. Here I can explain a bit more what is the green region. The green region is the location where the object is going to impact the atmosphere at 100 kilometers in altitude. Going on, here, again, zooming a bit, the red spots are actually the spots provided but actually from the website, from Paul Chodas. They are very well consistent, and here is more easily visible. Anyway, there are some caveats and conclusions. First of all, this is a purely dynamical tool, so there is no atmospheric interaction model including this. Maybe later on we will have time and resources to include also more sophisticated models. This tool is not meant for the public. It's meant for ESA in particular, and is actually ESA responsible to provide this information to the decision makers. As you know, if the probability is very low, we have this very long corridor, and of course we have to be careful to provide this information to the public. So the decision makers are actually the well-known entities. We start to compute the impact corridor. This is a requirement that we start to compute the impact corridor when the probability is higher than 1%. But of course, we are able also to provide this computation at lower probabilities, but it's not recommended because in this case, the semi-linear assumption may fail. The output should be, this is a personal recommendation, should be released to the public only when it is double-checked with other independent computation providers. There is NASA, of course, but also Ed Lu was actually describing that, telling me that they are also thinking about having the similar tool. And of course, it has to be agreed among all the players. The good thing of this tool is that it can provide an easy tool, an easy way to provide material for press releases for the media. And last thing is that using the KML format is a very flexible tool that can be overlapped with other layers like the population density among the planet and also the critical infrastructure map and so on and so forth. So yeah, that's it.
Thank you, Fabrizio. Other questions to this presentation? Yeah, wait for the microphone.
I want to stress what you said about being careful about releasing this without a bunch of pre-discussion first, especially with not just amongst people calculating it, but amongst the political powers, because of the fact that, again, if some of the things that we talked about during the scenario was the possible economic effects. So it could be quite sensitive information.
Are there other questions or comments? Yes, please.
Yeah, I guess I don't understand this not released to the public. Clearly, this is a sophisticated and better calculation, but many kinds of kids and students and people are capable of calculating these things, and it's not going to be held unreleased. Your calculation may be, but I just don't understand this business of releasing it only to decision makers, releasing it only to emergency managers that Detlef talked about at the second last bullet of his conclusions slide. I just don't see that as being realistic.
Yeah, I agree with you that it's very easy now that everything is published on the internet, and in a few minutes everybody is aware that it could hit, okay? But one thing is that one kid is releasing this on the web, and one other thing is that an official space agency is providing this kind of information. So we have to be sure, I mean, this is my opinion, but we have to be sure that for example, ESA and NASA and other players are agreeing in this computation. So
I think you just hit the key point there. There is, it turns out in the public eye, a quite strong distinction between an official announcement, release, press release, that kind of thing, versus something you just pick up off the web that you can believe or not. So I would strongly oppose any secrecy to actually attempt to hide it from the public, first of all, because it'll simply fail. But on the other hand, the idea of making an official announcement that the agencies are willing to stand behind, now that's what you would call a release, but you should just make sure that you keep that distinction clear.
Yeah, I mean, it's not my role to play this and to have this kind of responsibility. But one thing is to have a corridor that is 20,000 kilometers long, and to say this to the public. I mean, there can be consequences, panic consequences, economical consequences. I don't know. You have to be careful. Another thing is when the region is very well determined, very well constrained, then you have to communicate this to the public.
Okay, is there another comment? Maybe I could make one comment to this, because it was a tool developed for ESA. So the purpose is not to keep all these results secret. As you have seen, those numbers published here and others can be fully presented to the public. It's only in case of a real event that then we would inform the civil emergency protection agencies or others a little bit ahead. Because after that it will be decided when to release the results, that they get the information a little bit before. I think we should move on, and the next presentation will be given by, please, thanks again, by Victoria Friedensen, and the title is Deciding to Act, Summary of NASA's Planetary Defense Coordination Office Activities to Define Thresholds for Government Decisions to Aid in Emergency Preparedness and Response. Please.
Thank you. Do we get the longest title of talk award for the conference today? Thank you very much. It's a privilege to be here. I'm going to briefly summarize a couple of aspects of the activities that were undertaken at NASA in the past year related to planetary defense, specifically the initiation of the Planetary Defense Coordination Office, the initiation of an interagency working group, and where we are at looking at decision-making under uncertainty, and a few comments as we look forward to this year. Planetary Defense Coordination Office was officially established in January of 2016. And because we're late in the conference, it's Thursday afternoon, I put the takeaway items in red, okay? So ask your questions about those. At any rate, so PDCO was formalized. It includes the Near-Earth Observation, Near-Earth Object Observation Program, as well as several other new activities. The goal is to provide timely and accurate communication about potentially hazardous objects and to lead coordination of U.S. government planning for a response to an actual impact threat. This is a sort of a new job for NASA. One of the key functions of this is, of course, interagency coordination. I suspect any bureaucracy worldwide would have some aspects of this function. We stood up with the White House Office of Science and Technology Policy an interagency working group called Detecting and Mitigating the Impacts of Earthbound Near-Earth Objects, or DAMIAN. This interagency working group is comprised of 8 primary federal agencies and representation from 9 more. And it was convened to serve as an interagency body to define, coordinate, and oversee goals and programmatic priorities for federal science and technology investments. So what federal science and technology activities are is actually how the federal government spends the public funds on these topics. DAMIAN is also intended to provide Earth impact response and recovery input to the National Planning Framework for National Preparedness. This is a presidentially mandated activity to collate, understand, and estimate various risks and hazards that are out there that the federal government may have to respond to. So DAMIAN, the primary work that we completed was to write the National Near-Earth Object Preparedness Strategy. There are the usual goals you might expect: find them, characterize them, figure out a way that we can respond either through deflection or disruption by testing methodologies, improve our models and predictions. Differently is to develop emergency procedures for neo-impact scenarios. This would be the Department of Homeland Security's Federal Emergency Management Agency, or FEMA. Establish these procedures, leverage international support and coordination, and establish coordination and communication protocols and thresholds for taking action. This is a key step. It is part of that, who do you call when you need to, and what do we expect that they'll do. This is published on the web at the bottom, and you can also find it on the Planetary Defense webpage on the NASA government website. So, Damien, we developed decision flows to show the spectrum or the continuum of decisions that have to be made. This is not a one-step, one decision, one-step, one-decision process. It's highly iterative, starting with communication, coordinating, and determining thresholds, agreeing on those thresholds, developing and working internationally also on these thresholds, so communicating with I1 and same page, the United Nations, Committee on Peaceful Use of Outer Space, et cetera. In addition to all the other things that you would expect: modeling, detection, deflection, disruption. And then if there is indeed an impact that has not been prevented, then what we would do is engage to assist as we can in the response and the recovery. This leads to one of the key aspects that all of us have discussed today, over this past week, is uncertainty in decision making. Of course, in this case, uncertainties can be reduced by further observation. And I've put a chart from an Apophis study up there to illustrate how, with further observation, the initial assessment of the threat was gradually reduced over time, if you've got time to do that. Which feeds decisions on whether we can prevent this natural disaster or minimize the natural disaster. Shall we take the hit and rely on emergency preparedness, or make an attempt to deflect or disrupt? And which begs the question for federal investments is, how much uncertainty is acceptable, or how much certainty is required? This is, as we look at the different scenarios that have been discussed today and the different probabilities, at what point would you, would the federal government in the U.S. be expected to take action? And this involves spending public funds, okay, as well as understanding the processes. I think it was Nahum who noted that the longer you wait, the more expensive it gets. So what we did with Damien was we developed about 50 different scenarios that looked at different spots where you would have to make a decision, what the thresholds for the decision were, in which you could result in a happy ending or a sad ending. This is just one example of that whole suite of discussions. It was very interesting. The various players from the federal agencies that participated in Damien, what decision points they felt were important, the different perceptions of what a 1% probability meant, a 20% probability. So there was a great deal of discussion there within the working group as we were working to write the strategy. But in this idea of uncertainty and percentages is also has to come in is what does the public, what does the taxpayer, if you will, say? So NASA had sponsored an activity called ECAST, Expert and Citizen Assessment of Science and Technology. This was done in 2014, and the report came out in 2015, in which the participants were asked to assess a series of scenarios and then indicate their preferences. The discussion showed a safe rather than sorry preference. Let's take action under higher levels of or lower probabilities. The participants were offered a series of scenarios in in which probability of impact versus the size of the object, and generally the participants were conservative, i.e. erring on the side of taking advance action, meaning, yeah, we'll have to pay for it, but we believe this is an investment that's worthwhile. So with a 25% impact probability, respondents preferred to implement a deflection or disruption option for a regional size condition just in case, and we're certain that preventive measurements should be taken for a 75% probability. Now, I also have to explain that many of the respondents, majority of the respondents, were opposed to the use of nuclear weapons. They were opposed on moral grounds, and they were opposed on the perception of risk of the launch of the weapon. Okay, as the impactor and the probability rose, of course, that objection became slowly was reduced. However, there were still a trend in which there was send more impactors. Don't rely on nuclear, okay? We can afford the launches. So this kind of input contributing into how NASA's looking at Damien and at decision thresholds. Short or no warning events, depends short. We have, in this particular scenario, for this one, a relatively short, but we have the time to get some reconnaissance spacecraft off. In Paul Chodis's talk earlier today, you saw a scenario in which we had 4 years, and it was deemed not enough time to be able to launch a mitigation effort. So we were looking at this, and we were looking at what it would take for agencies to be able to invest in studies. So NEO impacts, because of these uncertainty conditions, NEO impacts are being assessed for addition to the Strategic National Risk Assessment so that the U.S. Department of Homeland Security can indeed develop specific emergency response plans. So you know we all have projects that are in preparation, planning, study phases. In order for the government to spend a certain amount of money, you must have the authority to do so. By adding asteroids to the national risk list, this now becomes a valid use of the public dollar, of course, appropriately applied. For a mid or a long-term warning, where we have the idea of uniquely preventing a natural hazard, this is an interesting concept for folks who are used to hurricanes and earthquakes, or mitigate the negative effects, the decision scenarios are deemed critical to guide public investment. The scenarios give the decision makers a sense of they have a chance to work through the scenario, gain a level of familiarity, understand a little bit more of the nuance, get a grip on the jargon, and be able to better later, if there is indeed a situation that comes up, to provide a basis for that guidance. Which leads us to I-1 and Same Page. Now, I-1 and Same Page have sort of led the pack in the development of the criteria and the thresholds. This is extremely useful. However, this is not a limitation, but the way I-1 and Same Page are set up for the United Nations, they shall warn, and phrases planning should begin and should start in planning. So what would happen then is organizations like in the US government or NASA would then take this guidance and start making investments. So looking forward, Damien's next task is to develop a national action plan. We have been a little bit delayed by the transition in government, but as the Office of Science and Technology Policy is being reformulated, we hope to move forward in the near future, and the primary goal will be to develop a set of thresholds to aid in decisions whether to prevent or to mitigate a threat from an impact. Thank you, and I'll take any questions.
Thank you, Victoria. Other questions or comments to this presentation?
That one or this one, same page? Yeah.
Yes, please, Boris.
First short question, just for curiosity. What are the other 6 agencies? You mentioned 8.
Okay. The list? Okay.
Yeah, just to realize what.
So,
what
for example, the Department of Energy, the Department of Homeland Security, the Department of State, the Department of Defense, Department of Commerce. Lindley, am I leaving any out here?
And State Secretary Department, no? That's
The Department of State, yes.
Okay.
Okay,
State, yes.
et cetera. And then minor other organizations like the National Science Foundation, the U.S. Geological Survey, for example, all participated.
And the question that you had just mentioned that Damian is in progress. Now, what you see, what is the level of major decision maker? Because that's, for instance, NASA had a fiscal year fixed. They should spend another $500 million for suddenly, not expected beforehand. So somebody should take this responsibility. Same for FEMA and so on and so on. It should be some governmental decision to start these costly programs. What do you think? Which level you require? Special body or existing bodies or president or Congress? I don't know what.
The way we're set up right now, Damien consists of senior undersecretary level participants. Of course, NASA's not cabinet level, but senior members of the agencies that can make commitments, the due process, of course, to arrive at those commitments. In the event of something, it is deemed that it would be a collaborative effort. We would be convened probably by the White House, which would call a special action team to do this with representatives from the agencies. Did I answer your question?
It should be a special body. Not a special body should be established.
Oh, a special independent body established and standing up?
Yeah.
Oh, I'll take that under consideration.
Okay, is there another short question or comment? Yes, so one last.
Thank you. Regarding the special body, all the student groups I've met in last 2 years regarding planetary defense, every single one proposed special body on a global level regarding planetary defense decision making, just to mention.
Yes, and in fact, ECAST said the same thing. The ECAST participants all thought that there should be a special independent trusted advisor to manage this, one that has an independent stance. So.
And who will make the decision to launch something then?
So we're kind of working through this in the scenario, aren't we? But roughly, it will depend on who is making the contribution. As Avi pointed out in the first paper, each nation retains its ability to make its own decisions. So I think that we would be understanding this almost on a case-by-case basis, and that it would not perhaps be wise to have a one-size-fits-all rule at this time. But there are plenty of corollaries there that could be used as a precedent for all kinds of responses.
Okay, I have one short comment on this from Lindley, and then we have to
I just
move
want to
on.
make one thing clear. Damien is not a decision-making body or anything like that. Damien is just an interagency working group with the U.S. government for us to start to work out our planning and what agencies can contribute to the mission, largely under existing programs. When it comes to an actual threat detected, that enters a whole different realm of actions on the part of the government. And in the U.S., it would probably be done by the Office of the President setting up an emergency response team.
Okay, thank you. I think we have to move on. Let's thank the speaker again. So the next presentation will be given by Andrea Milani, and the title is Measuring the Performance of Impact Monitoring. Please, Andrea.
How do I change the page?
This one.
Okay. 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 This is my title, my presentation. I would like to give you a key of how to listen and read. The purpose of this talk is to give you the concepts and to make you perceive that there is a strong mathematical theory behind it, but you are not, my suggestion is that you don't read the formulas. The important thing that you know that they are there somewhere, okay? So as an example, what is the confidence region? You consider the ensemble of all the conceivable orbits of space objects. The confidence region is a subset of this piece of this space of the orbit which are possible because they are compatible with the observations. There is a formula defining this, but you don't really care about it. Oh, this doesn't show. Okay? This is the formula, but it doesn't matter. Now, what is impact monitoring? Impact monitoring means to establish whether inside this confidence region of possible orbits, there are some orbits which impact the Earth. I need to stress that if this fails or is achieved too late, essentially none of the things we've been talking about in this meeting can occur. All the simulation discussions start from the fact that you get a warning. If the warning is not there, mitigation not only does not even have the honor of failing, is not attempted. So it is necessary not to give completely for granted that this warning is available. By the way, until when they discovered how to do this only 18 years ago, nobody knew how to do this. First definition, what is a virtual impactor? A virtual impactor is a piece of the confidence region, the possible orbit, connected, that is, patched together, which leads to impact on the Earth on a given time. The purpose, of course, is to discover virtual impactors inside the confidence region. Because the confidence region is large and the virtual impactors are small, the problem is how you do this. And so, apart from some easy cases, the way you do it, you use virtual asteroids, that is a finite but possibly large number of orbits selected by some criterion inside the confidence region that is among the possible ones, hoping that one of them is close to the virtual impactor. As it is rather obvious, it's not trivial to decide how to select these multiple orbits. Now, again, in this case, I've not even written the formula because it would take a couple of pages. There is a definition which I've not given to you, by which it is possible to define a one-dimensional line in such a way that all the points on the confidence region are near enough to this line. It's like if the confidence region is a snake and you use the spine of the snake. And this does not work always, but works in 99% of the cases. If we have this line of variation, we just sample this line by a finite, but maybe large, 1,000 points. As an example, if sigma is the parameter of this line, we use a constant interval in this parameter. This is one possibility which we were using until a couple of years ago. Then each one of these points corresponds to a virtual asteroid. That is one asteroid which is possible, which is at least near to the reality, but you don't know which one. And you propagate each of these for some time in the future, like 100 years in the future. The target, then, you store information of the close approaches which occur in the meantime. And then you represent them in a target plane, which is, roughly speaking, like a target of a dart exercise. It's a plane passing from the center of the Earth perpendicular to the direction from which asteroids are coming. And you get something like this. These are the individual virtual asteroids, okay? Now, how we measure the efficiency of impact monitoring? By defining something, we have invented this name, generic completeness limit, is the highest impact probability for a VI that could possibly escape detection. And this by using an approximation that the trail on target plane is linear. So if you assume that the line of variation is a line, then these are the individual points. In this case, in this disk which defines the close approach, we have 4 elements of this sample in this ensemble. Now, the method will certainly fail if you have one here and the next one is here. That is, if you have no points on the target plane. Okay? Now, let's suppose for the moment that one point on the target plane is enough for detect for EBI. Then there is a way, again, I'm skipping the formulas, by using some derivative, like this one we call the stretching, to find out what is the condition to have at least one point in the target plane. And then, again, there are a number of formulas on which I skip. By knowing a little bit of probability, you find out what is the corresponding probability. In particular, for what we were doing until 2 years ago, we're using 2,400 virtual asteroids. That is, we're computing for 100 years, 2,400 orbits, and the impact probability critical for detection was 4 × 10⁻⁷. Now, the question is, does this work? This figure shows, as a function of this stretching quantity, which I've defined before, how many virtual impactors you find, and you see a nice power law growth, which more or less stops here. This here corresponds to 2 virtual asteroids in the target plane, which means in reality between 2 and 1, we have a loss of efficiency. So in reality, our results are more similar to assuming 2 points on the target plane. Okay? After that, you have probabilistic detection. That is, it's not that there aren't virtual impactors here. It's that our system has not enough resolution to detect it. Okay. Now, given that this was the situation, what are we supposed to do to improve on this? Well, we want to decrease the value of this critical probability by a factor, as an example, a factor 4. Why a factor 4? Because you know that there are 2 impact monitoring systems, one at the University of Pisa and one at JPL. The one of JPL was already working at the level corresponding to 10⁻⁷. We were, to some extent, 4 times less efficient, and therefore we just wanted to be aligned with JPL. Also for the very good reason, otherwise it would be difficult to compare the results. And also we would like to fill the loss of efficiency for a case with only single virtual asteroid. The solution is essentially to use optimally spaced points in such a way that the probability between any 2 of them is exactly the critical probability. So while previously this is the step size as a function of the value of parameter sigma, previously we were using a constant one, and later we are using one which depends upon the probability density. And as a consequence, we get to be more efficient. So in particular, we can get to the limiting probability 10⁻⁷ with only about 4,800 points. Again, at this time, since this method is tuned really to probability, not to this arbitrary quantity stretching, so this is actually minus the logarithm of impact probability. So this 7 here, this orange line corresponds to the critical generic completeness limit. And again, you see pretty well that up to twice this value, we are pretty well off. We have a nice power law growth. And by the way, the exponent of the inverse probability is 2/3. Not that we don't know the meaning of this 2/3. Must be some kind of fractal property. And after that, we have a decrease. And this decrease corresponds to the fact that the others have a probability of being detected, which essentially the ratio, yes, okay. Now, an important advantage of having aligned the generic completeness limit with the JPL is that now we can make a comparison, which is whether really we are obtaining the same results. Not only in quantitative sense, but also comparing one by one the virtual impactors obtained at Pisa and obtained at Pasadena. Now, we can do this only for probabilities which are above the critical value. The other results are probabilistic. So the probabilistic result cannot be aligned. I mean, if we launch dices in Pasadena and then launch dices in Pisa, we cannot get the same numbers coming out, isn't it? While for something which is deterministic, we can make a comparison. Therefore, we have we found 19 differences, which are a bit too many, but then with some work, we found out good explanation for most of them. Currently, we have reduced the difference to 5 cases. And maybe this can be improved too. Conclusions. Maybe I have to explain one background fact. It is not the case that previously the results obtained from PISA from JPL were discordant. There was an agreement by which we were not allowed to publish discordant results for the most critical cases. This was even imposed to us by the International Astronomical Union. The concept is that for everything which was above the Palermo scale, -2, which roughly speaking corresponds to 1% of the background risk for impacts of the same energy, there was a consultation requirement that we have to first cross-check between PISA and JPL and be in agreement before making this public. And if necessary, withdraw publication until when we manage to get in agreement. This was a little complicated also because of time zone difference. And this was done entirely manually, but these were a few cases. Now, we have pushed our impact generic completeness at the same level of JPL. We've increased a little bit the computer resources. Now we can make the comparison. And we have done this comparison as a once in a while effort, and we found discrepancy are less than 1% of the total list of asteroids with virtual impactors. But now it becomes possible, and we try to work on this in the future, to make this comparison automatic and continuous. In such a way, we'll have agreement not to the Palermo scale -2, but to 10 to -7 impact probability level. And this should give some confidence that even announcements at comparatively low probability are to be considered reliable. Thank you.
Yep. Thank you, Andrea. Are there questions or comments to this presentation? Yes, please.
I was wondering, for the problematic cases, the few cases where you have different probability of impact, can you run a brute force approach, like a Monte Carlo, and check, or is it out of the computation limits of availability?
For few exceptional cases, we can always do that. However, to run systematically Monte Carlo runs, we cannot do, because the Monte Carlo runs are always possible. They are about 1,000 times more expensive in CPU time. And therefore, we cannot do this every day, roughly speaking. So we need to be able to concentrate the cross-verification to a few critical cases, in which case it might be worth investigating to find whether there is some bug or some difference, which is important.
Are there other questions or comments? If not, let's thank the speaker again. And we now come to the last presentation of this session. It will be given by Nikola Schmidt. And the title is Strengthening Global Collaboration and Reducing the Risk of Defection of a Cooperating Nation in Planetary Defense.
Okay, thank you very much. Thank you very much for the opportunity to be here. It's really great now. After 2 years now, I've become passionate in politics of planetary defense. We started this session with a very good rational approach now. So let me end the session with a hopefully also good irrational approach now. Because international relations, and especially theory of international relations, can be very easily divided into 2 branches, the rational, let's say, approaches and the irrational approaches. What I'm trying to present here is that these irrational, which might be finally, very valid and thoughtful critical approaches, can use or can do some good, but can do also something bad now. And what we are currently doing here, we are creating an issue of security on the international or global level, and it can be criticized. So let's say the principal objective of the presentation is to take this theory and apply it to what we are currently doing, in order to not be criticized and develop policy and especially narrative that will simply help us to communicate our point appropriately. So the presentation objectives are simply to apply the theories of international relations that will finally for sure study and influence what will be the policy of planetary defense and what will be planetary defense as a security issue. So I divide it into 3 points: how to properly communicate our what I call desirable argument, how to make planetary defense a political feasible endeavor, and how to keep the design infrastructure sustainable. That's the method how to avoid defection of cooperating nations. So what are the perceptions? I mean perceptions how we currently communicate planetary defense. So we think that we possess the technology to do so, so it's a moral obligation to approach it. However, some kind of technology doesn't seem to be fully moral if it is applied in a different manner than planetary defense. It is an opportunity for unprecedented global collaboration. On one hand, we call for global collaboration for planetary defense. Now, what I'm trying to say that it's much more an opportunity for that global collaboration. A global agenda that has the potential to fade out national differences and promote something what I call cosmopolitan mindset. We all the time talk about that we simply need consensus, that it's a global or international, because without defection risk, so finally unprecedented consensus, that's a cosmopolitan mindset. An opportunity to deepen the credibility of liberal democratic agenda, of course. We don't want to be deflected by certain states like probably North Korea. We also see it in the exercise that there is simply no way. On the other hand, if we have to apply cosmopolitan mindset, we should simply put everybody together. So no Korea is doing it on themselves. Planetary defense can be enabling path-defining endeavor for human flourishing. That's the ethical argument. So what planetary defense in this perspective finally is? It is a security issue par excellence. So it's simply unavoidable that it's going to be studied by critical security studies. It's a global security challenge, however, in interstate political system. So we need global approaches to something what we have to apply in international state political system. So we need to take it into consideration, and that's not, easy to simply design policy which will be accepted by these political entities. So the way forward, which I'm somehow taking from a current or recent rearticulation of critical studies theory, is that we have to make a global ethical security cause. What does it mean? At the beginning, before I proceed, currently we talk about policy ideas that finally solve planetary threats. What I think is the better approach, that we simply think what are the ideas behind planetary defense that can finally enable not just the policy to defend Earth, but policy which might have broader considerations or broader applications. So we can call it a desirable broader policy, desirable for that human flourishing. So now a little bit of theory which I'm applying. How world politics should be studied. Robert Cox in 1980s, it might seem to be self-evident, but that time was a very significant switch in the research in international relations. Until then, for decades, scholars in international relations were thinking about problems and how to solve them. Since then, since 80s, the critical approach started to be very influential, and they started asking questions like how the order came about, how the problem was set up, how the institutions gained power in order to tackle with threats, which finally are not, statistically so important threats. Just imagine, a nice example which has been said for thousands times is the comparison of people who died in car accident and people who died thanks to or due to the terrorist attacks. How many people are paid to tackle with terrorist attacks and how many people are paid to tackle with car accidents? That's what critical security studies are studying. However, they are going to study us now. Yeah. So let's combine them. Let's make a solution how to avoid that criticism which is not desirable for enabling planetary defense. Security studies would study planetary defense as a security to be solved. Critical, to whom will planetary defense benefit? But ethical security studies, which have emerged about 5 years ago only, are talking about global security issues which are worth to be talked about, which are worth to be solved. So how something become a security issue? This is just an example how influential that thoughts were in 1998, because 5,000 citations, only one book was capable to produce, so you just can imagine how influential the approach in international relations have been recently. So in a nutshell, what they are saying, a selected issue that is not related to security has been securitized as an existential threat. What we are doing here, we are saying that asteroid is as an existential threat. We need to survive, so we need to solve it. To the referent object, that's the humanity. By the securitizing actor, that's the group of experts, epistemic communities. To the audience, that's our decision makers, and thus after the process understood as a security of issue, because that's our desirable outcome, that we will have between decision makers planetary defense as a security issue worth to be, securitized. However, the same people finally said that the only right approach is desecuritization. The problem is that they were referring to security issues related to national security, not to global security. And national security within on an international level means insecurity in the global level. If one particular nation thinks that something is insecurity to them, it might be security to the others. So how to proceed before we detect the asteroid? Before the threat materialized, and we can with 100% certainty say the threat is there and we need to securitize and act. And that's what happened, what started happening since 2011. Rita Floyd somehow came up with 3 conditions. One of the conditions is the threat must be objective. So what is behind the objectiveness? It's amazing on asteroid. We can simply measure it. We can say the asteroid is there. So it's not culturally bound. It's much more naturally bound. You can say the terrorist is going to kill us because he said it. Okay, but he can change mind. So, it's not appropriate or say objective threat. So the reaction would not be based on 100% certainty. Security of the referent object must be morally legitimate. So what that means she talked about survival. She talked about profit. She talked about solar system expansion. In general, she talked about human well-being. Some others started talking about human flourishing. The security response must be appropriate in the relation to the aggressor, and the security actor must have sincere intentions. Appropriate means we have means to tackle with asteroids which are not going to cause political distrust on the international level. Let's take this deflection. That's the idea behind nuclear weapons. We know that there are nuclear weapons, but we personally are saying, please talk about nuclear deflection devices. The world will call them nuclear weapons which were launched to the space to deflect the asteroid. And then we are going to be in a world that the asteroid is deflected, but nuclear weapons are in space, and we will have to tackle with that word. Sincere intentions. And then we were talking about planetary defense site, which is on the far side of the moon that does not threaten Earth, direct energy, which cannot be round back to the Earth, etc. So how to talk about the ethical cost? Jonna Niemann divided security into negative and positive security. She based it on the recent theoretical debate in certain journals. What I see in planetary defense community is that we are limited to the analytical frame and negative security. We all the time talk about the absence of threat. However, what I think is much more desirable to us to build the argument is that the normative frame and the positive security. And that's what I saw yesterday in the DART mission statement. Contributes valuable data to many disciplines, planetary defense, science, human exploration, and resource utilization. I think this is the key to simply starting talking about commercial infrastructure in space which can be enabled for planetary defense if needed, instead of deploying planetary defense somewhere in space and try to defend it against the criticism. Because what will happen? What happened in 2013 when something was signed between Russia and Obama? Very well and renowned and respected scholar Jeffrey Roos immediately wrote this article that supremely bad US-Russian plan to nuke asteroids, only because the treaty contained the point of the asteroids. He missed another point, but we don't have time. I have 1 minute and I'm not at the end. So let's move forward. Policy architecture, which just an idea. I don't think so. It's, let's say, easily applicable, but I think it's the way how we should think. So at the beginning, we are talking about the desirable argument. Its desirability. Path-defining ethical cause, planetary defense, not as an absence of threat, but planetary defense as an ethical cause, because it's the condition for further human kind flourishing. Just cause, objective case. We can measure it, so we can say there's 100% certainty that it's going to happen. Enabling condition for human flourishing, no limit to absence of threat. However, then it's about the feasibility. Let's talk about acceptable technology then. Because if the acceptable technology can enable that hormone flourishing, it's feasible instead of, let's say, talking about let's deploy the nuclear weapons because it's necessary then. Then involvement, the sustainability. Then. Technological interdependence. Now, since 70s, the neoliberal agenda simply raised the argument that commercialization of the world will somehow imply cooperation between nations. Technological interdependence, International Space Station, ITER, or LHC, these are the examples that large technical complexes simply contain, somebody of you said madmen, yeah? People who might tend to defect from adopted projects. So, and sorry, I have 17 seconds to explain this. The idea behind it is that we have detection, development, and deployment. And every single phase has a different level of confidence. However, every single phase enables higher level confidence. So at the beginning, when we share the data, it's not a problem for nations to share the data. Then we can develop the technology which will be enabling to deepen the confidence between the nation. And then we can think about deploying technology which is currently more problematic than it will be. It won't be problematic that time. And yeah, okay. So I wrote an extensive article based on this presentation. So yeah, if you are interested more, I will be outside now, and I'm ready for your questions now. Thank you very much.
Thank you, Nikola. Are there comments or questions to this presentation? Yes, please.
Thank you very much for your speech. And I completely agree with your idea on the global security ethics. Thank you very much. So my question is how to realize your idea in this planet. Here in Japan, we are now expecting the United Nations role in this regard. So my question is, how do you realize this? And if you have any idea to strengthen the United Nations activities in this regard, please suggest us.
Yeah, this is a Nobel Prize question. On one hand, it looks like a theory, maybe a wishful thinking. On the other hand, it's exactly what happened with Paris Agreement. Paris Agreement is based strictly only on mainly only on the tool which is called name and shame. If a nation decides defect from Paris Agreement, they are going to be named and shamed. That's all. Maybe, that's enough. It's called social constructivism. We simply stick to norms. States tend to behave according to norms because then their behavior is more expectable. We can expect their behavior better. And that's a whole branch of international relations. To what extent norms in international relations in fact influence the behavior of states? Paris Agreement is going to tell us how much norms can be influential, but yeah, I like this kind of research because it's based on ideas. It's based on ideas which are dating several hundreds years ago, and they are somehow fulfilling to some extent because these influential thinkers simply were capable to influence. Just remember the politics in the 19th and 20th century. After what said Immanuel Kant, after ideas like Machiavelli, a couple of years before Immanuel Kant. Yeah.
Are there other questions or comments? Yes, please, Romana. Could you bring her the microphone?
Yeah, thanks, Nikola. Very briefly, because I also come from the same international relations background, so it's interesting for me to see it applying IR theories on the planetary defense and the policy and setting up an infrastructure for decision making. What struck me yesterday when I saw some of the comments from the public when we did the exercise is the question, would the affected countries, in the case of a credible threat, vest their power into the Security Council, where you have a veto power of the 5 permanent members for a decision, for example, to have a nuclear device on? Yeah. launched. So in your opinion, when you did this study, so what would be then a credible sort of final decision maker, or will this go back to the nation states or the affected nation states? Thanks.
I don't want to make it too complicated, but I would argue that nuclear weapons in space, thanks to that norm in Outer Space Treaty, thanks to the norm in PTBT and partial nuclear ban treaty or whatever, it's simply materialized that norm that nuclear weapons in space are simply taboo. And there has been an extensive research in the 90s related to chemical weapons and why chemical weapons haven't been used for centuries in battle, why even Hitler didn't use it. And even, Immanuel Kant in that Perpetual Peace was talking about poisons as something what is taboo. So it was years-long taboo. And that taboo was violated in the First World War. Despite the fact that it was adopted several years ago, it's not possible. And it, sparked new discussions and more tough treaties that chemical weapons simply haven't been used in the Second World War. And I would just say, if we use nuclear weapons in space, it's going to break this taboo. And I would just, start talking about what's going to happen then if we break this taboo, and if we would like to live in that world, or if it's not, more desirable to simply build planetary defense, which would be based more on, let's say, kinetic impactors, or the readiness of kinetic impactors on the commercial infrastructure, which can be used for kinetic impactors, or direct energy on the far side of the moon, which can be used for mining, etc., and flourishing humankind, etc. So I don't think so. This is a framework for decision making. I think it's a much more approach to develop an ethical narrative behind planetary defense, not to be blamed by critical scholars that we are trying to destigmatize nuclear weapons in order to defend planet Earth. That's, I think, the risk behind it, and I think we should avoid it.
Okay, thank you. I think we should stop the session now, and let's thank all speakers again. We have now a coffee break. Of course, you can use that also to contact one of the authors of the last session. And I suggest we reconvene at 5 minutes past 4 o'clock.